So this is just, I am taking the schedule what we teaching plan. Let's go over a little bit on this with respect to basic thread of how all the topics are integrated together. In my opinion, some of them require much more focus. Starting with, let's say, the one on costs, because that is going to be really the fundamental base on which, if you pursue a career in companies and industries, that will come through lifelong. So to have a good understanding of what is meant by a cost is very, very important and essential. So that is lecture notes. It might be useful for you to periodically go through and go through it. It's actually very simple. For a person who is technically good, this cost business should not be at all a problem. Though there is a lot of hype being made about cost and so on like that. If you cut all that irrelevant things, core is very simple. Basically, what resources you are using, how much quantity, what is the cost in which you are making the resource available at the point of consumption. At the point of consumption, not somewhere. So with this, you will find, let's say tomorrow you are in a plant located in location A, a similar plant is located in location B, you will be able to know what is the likely cost differences between the two. It may be the same technology, using the same kind of raw material, same capacities, everything may be identical, but the locations will make a difference because the cost of delivering the raw materials and cost of taking away the finished product will vary from side to side. So that is one simple. Leaving alone the financial wizardry like locational based tax advantages and whatever, let's ignore that part. So basically, cost is something which I think it is very useful for you to go through that. But it's a very simple thing. Variable cost, fixed cost, how do they vary? So that is something which you can again go through. Related to that is this bit on finance. How finance is different from cost is, after you understood what is the cost of the product, the two questions which will come: how much does the product cost to make, and what is the cost of setting up a plant to make that product. Of course, some details you have to fill in. When you say cost of the product, you have to know the technology, and capacity you have to give in order to tell you how much will be the unit cost of making the product. Now, central to this as an engineer, how does he relate is the importance of flow diagrams. In one of the lectures, I jokingly said, normally there is a session on, I think, chemical process technology or whatever you call it. There is a Shreve, Norton, all that used to be there. It is actually a bore, because till that time you will be concentrating on other subjects, on concepts. Here is something which is a history being told. This is made like this, and so people casually go through the flow diagram and skip it, which is perfectly alright, understandable. But at some point of time, you have to relook at this flow diagram in a much more different way of what it conveys. So every picture in the flow diagram is important, every line in the flow diagram is important. So that is the central part. So if you look at the flow diagram, I gave the example of ammonia, right? Ammonia making, it's a horrendous mess. Some blocks here and there and lines connecting all over the place, and if you can't even trace it in the first attempt from A to B, you can't even trace it. There are so many lines. But if you get the hang of that and spend more time on this, the question of cost becomes very clear. Because if you know what are the operations being carried out starting from raw material to finished product, the flow diagram will capture that in essence. So with that, and with the flow diagram, meaning flow diagram always goes with energy and material balance. You must have that complete. Otherwise the flow diagram is incomplete, it's just a sketch. So if you have the flow diagram along with the heat and energy balance, you will get a very good estimate about the variable cost of the product at least. Some confusion will be with respect to utilities, because the flow diagram will give you the raw materials flow and so on like that, but how much electrical energy is required, for example, depends on the specific nature of the equipment, what pumps, capacities and so on. But that is a second detail, but at least you will get a very good idea about how much does it cost to make a product based on the flow diagram. And of course the flow diagram is absolutely dependent on the technology that you have chosen to make the product. So that is the link between understanding the cost, looking at the flow diagram and getting to know a hang of what is the variable cost like. Even fixed costs, which is the second question, which is how much does it cost to make a plant to make a product of a certain capacity, is you can derive a lot of information from this flow diagram. Because first, of course, you will know what are all the pieces of equipment that is required. Flow diagram will capture right from raw material. In fact, a good flow diagram will capture from raw material storage. In one of the first lectures, we jokingly talked about this Velachery plant, which is used to make hand sanitizers, right? So I said isopropyl alcohol. So we have to think of isopropyl alcohol comes in tankers, road tankers, ISO containers, where will you store? All that will add up to the capital and operating cost. So flow diagram part is very critical. We have not covered that in great detail because if I take one flow diagram, it will be 3-4 lectures, and there is no concept there. It is just only a detail that we have to work it out. So do spend some time. Take a process that you are familiar with. Don't take too complicated. Simple things like acetic acid, sulfuric acid, these things, simple flow diagram. Spend some time, this time looking at saying that do I get meaning of variable cost and investment cost by looking at the flow diagram, and also speculate what could be technology improvements possible, because slowly we will go from given technology to improved technology. We have to go through something has to be different in the flow diagram, right? Eventually the flow diagram has to reflect a change. So that is a key point on that. Now switching on cost flow diagram to finance. Finance is very simple. Basically it is a performance indicator, financial performance indicator of companies. So it is very, very key. Every company is driven by that at some point of time or other. As we are now discussing even in software industries, at one point of time, all the startups and so on, growth was the big thing. That if you had somebody viewing your website, 100,000 views, good thing going. If it became 200,000 views, even better. But slowly after some time, maybe 5 years, 6 years, somebody will keep asking, that's fine, but till now you have burned so much of cash, when am I going to get surplus cash? So all these indicators finally will have to translate into financial indicators, and that's the meaning of finance. We talked about very simple things like return on capital employed, how much investment you have made, and on which how much after meeting all your costs and everything, what is the surplus that you get, and that comparison, trend, comparison with other companies, comparison with industry norms, all that goes through. So that's about the finance. The next part was, at this point it was ripe enough to us to look at how does Indian chemical companies in general vis-a-vis chemical companies elsewhere stack up. This is very relevant, at least in your generation is going to be more relevant, because in the past and even now in some form or other, people are saying we will stay away from rest of the people, we will be self-sufficient. It's a good thing thinking, but experience says over a period of time there will be invariably some integration will take place. The amount of integration will vary depending on the societal expectations, pressures, whatever, but you can't live in absolute isolation going back to the Chinas of 1800s. It's not possible. So it's important to know what are the characteristics of Indian chemical companies, what is the constraints, opportunities in which they operate, and what are the, so that is a very rich information is there in those slides. Take some time, especially when you are nearing interview times with the companies. That's very useful to get to know how these guys think, because that sets the thinking of the companies, how they respond to that. So you will be better informed if you went through that. Then we talked about R&D, technology development. At this point there is a fork. R&D can be for the purpose of because you enjoy R&D. R&D can be for the purpose of because you want to make something better. Sometimes they can run together, but it is better to think them as two different paths. So you have to internally sort of explore and find out what sort of a person you are, what is your drive, what is your ambition, what makes you happy, and so on, and choose A or B. Because in research, pure research, which I call it more like academic researches, you do because there is a problem that you are interested in and it excites you, and therefore you want to get to know more about it. That is the path you choose. The other extreme, just for comparison, is there is something which is existing. That existing is very clear. So that defines, in some ways, it may even constrain you, because you are only starting with the existing. So you are to some extent shutting your mind off as what is possible. John Kennedy famously said, I think of, people think why when looking at this thing, I imagine and say why not. So this is very important also, but you have to sort of at least be conscious at that point of time what you are about. So this R&D, there is again lot of information is available. You can choose to read it and decide. When it comes to technology development, which is now here definitely there is an application, because it is not only generating, creating, understanding more fundamental knowledge, it is applying that knowledge for a end use which is defined by some customer. So money comes into the picture in technology. Till the time research, you can stay away. Money when it comes to technology, we talked about, and this is again going back to Indian companies, global companies. Why technology investment? How is it done? Is it developed technology in-house or you buy over, pluses and minuses? I think we went through that. That's an important thing to recap and go through that. We also touched upon patenting at that point of time. You get some intellectual property, then you want to secure it, and then subsequently what happens? We went through that. Then we spent little more time on, because this is the key issue again, increasingly there is a lot of, not increasingly, generally there is a huge confusion about what is technology. People, it's as if, somebody who knows only Swahili and somebody who knows only Hindi are talking to each other. So each one, what is technology development means? There must be a agreed framework. It flows from this idea to finally a plant which is turning out the product in an efficient. So at some stage where it is, there must be some consensus. It's not a scientific thing, but it is a agreed upon proper consensus. So we went through the fact that TRL developed in NASA, which is not a commercial enterprise anyway, and then how European Union has adapted it to their requirements, and how, this is an important point, how in India, at least Indian chemical industry, as of now, there is no consensus of what is meant by TRL. You can pretty much choose to define what you want to say, so beware of that TRL. But you got some idea, we went through those examples and all that. Then there were a couple of practical examples of technology development. Technology development, from here the course took a view that you look at existing, because any product, already there is a current way of doing it. So look at the, study it, meaning you have to go through the flow diagram, P&I, everything, understand how much will it cost to make from that product using that technology, how much will be the investment cost, and then what are the opportunities for delta. So that is what we gave lot of examples. Caustic soda we spoke, water as a practical example I went through. We talked about gasification, not primary reforming, secondary reforming, auto reforming, that sort of a thing we talked about and so on. Then we had external speakers coming in sharing their perspective of what it is to have a career in industry, what sort of a problems and challenges that they face, to give you a glimpse of what life is like that. Right. Now, the last few classes I went through Professor Narajan's notes also. Jobs and career path, there is again a huge amount of information. This is an important deck that you should keep it and periodically go through that. One other thing I noticed is, a lot of people miss those lectures. That concerns me a lot. So I don't know how to reach out to them and say, because sometimes the gems are hidden. You might very easily miss it saying that there is nothing in it. So that notes has a lot to do with what do you really expect and how you can make a difference. So go through that. Now that is what we have done. What I thought I will do for the rest of the classes is, today's class was supposed to be this, so maybe in another 2 minutes I will stop and hand it over. The next few classes will be, I am going to talk about how to prepare for job interviews in terms of identifying where you want to work, pros and cons, and a backup plan. And then A, backup plan B, how do you go prepare yourself for facing interviews, tests and things like that. I am also going to get two people. One is a student like you who took this course and who passed out from this institution, chemical engineer. He is working in some company outside. So he has agreed to share his experience, how he went about doing that. So he will come on a video call like that. I think I will announce the date. We can interact with him and figure out from. That's one. Secondly, I am going to get another senior colleague. He was the head of engineering of a EPCM company, engineering company, which recruits a large number of people. And he says his experience of 35 years, how he trained engineers, and what is he looking for in newer engineers, and what sort of a. So he will come with some prepared speech, but he says more like I will answer questions. So these two will happen. Then we are going to have this projects presentation by you. I think enough I have talked about the project presentation. If you still 5 days, 6 days, please complete it on 10th. I know that you are under pressure, a lot of things, but if you delay it on 10th, then the pressure gets transferred to me. I will not be able to do justice to your evaluation, because we need to read your reports, internally discuss. I have also asked some people from outside who came for this external thing. They are also very keen to understand. So we have to prepare them and then have this presentation. So complete it on 10th. So that is all I wanted to speak about this class.
Good morning. So I want to continue from the last lecture. So we talked about Taguchi's contributions to quality engineering, quality definition, quality control. And if you recall, one of the key definitions was regarding this cost of quality. Basically, Taguchi's view is when you're running a process to make a product, and there is a key feature of the product or a key property of the product that customers look for, then that product, that key property should be held as close to its ideal value or target value as possible. He basically said it's not sufficient if you have spec limits. Just because your product is within specs, it doesn't mean it's a quality product. It's not sufficient if you do SPC, statistical process control, establish control limits and all that. Even if it is within control limits, it's not a quality product. A quality product is one which is exactly at its target value or its ideal value that the customers want to see, right? So he says, if you deviate even slightly from that ideal value, there is a cost. And that's what he called the cost of quality. And he said it increases very rapidly as you move away from this target value. And he proposed a quadratic function as a default function. However, there could be some products where the behavior could even be exponential. As soon as you move away even a little bit from your target value, the customer dissatisfaction grows exponentially, right? What are some examples? Again, I think delivery time. You have something being delivered by Dunzo or Zomato or whatever. If you're supposed to get it within 20 minutes and they take 21 minutes, you're very, very unhappy, right? So it just takes off and you start, if you come 5 minutes later, you start yelling at the delivery person. So that's a classic example. And so he said, in order to satisfy customers, this so-called cost of quality should be at 0. And you have to do whatever it takes to return it to that 0 value. So if it means continuously tweaking your process, do it. Continuously replacing your tools, do it. Which is a very, I think, one-sided view of a process. He says maintain quality at whatever cost. But that's not a realistic view, right? You also have to think about the cost of manufacturing. If you have to continuously tweak your process to bring it back to its ideal value, rather than letting it drift between certain statistical control limits, there is a huge cost associated with that. There are people constantly on the manufacturing line fine-tuning the process to return it to its ideal value. So let's say we call that cost of manufacturing. Then the right view, if you want to do a real process optimization, taking both quality as well as manufacturing cost into consideration, is to define, certainly you can define a quality cost function, right? You can call it C subscript Q, and there can be some constant K subscript Q times Y minus M, where Y is your actual value of the parameter in your production, M is your ideal value. You can non-dimensionalize it by dividing by 6 sigma, where sigma is the standard deviation. And then you can raise it to the power 2m, where m can be 1 if it's a quadratic function, or it can be any number, if you want to give it a stronger dependence. And similarly, you can define a general power law model for cost of manufacturing, but now this has to be in terms of tolerances. So here, the cost of manufacturing, you can define again as some constant km times 1 minus y minus m divided by 6 sigma to the power 2n. So what we are saying here is actually the cost of manufacturing decreases as you move away from the ideal value, because it takes additional effort to constantly push your process back to its ideal or target value. So it's almost the reverse of cost of quality, right? Of course, these are power law models, but depending on the particular industrial process, maybe polynomial models are possible. So you can do some analysis of your process data and really come up with the right model for CQ and CM. But the point is, you have to be able to define a cost of quality which penalizes you for moving away from the target value, and a cost of manufacturing which penalizes you for staying close to the target value. And define a total cost as simply CQ plus CM, and do classical, minimization kind of strategy. And find the optimum Y. Where is the optimum setting that will minimize this total cost for my process? It may be not at the target value, it may be 5% away from the target value or 10% away. But the thing is, you have to do this analysis to identify that optimum setting for that parameter. And clearly, the critical parameters are the constants KQ and KM and the exponents M and N. So you can treat those as, actually you can even do a sensitivity analysis on M and N. If you don't know the exact form of the CQ and CM functions, you can treat these as unknown parameters and do optimization for various values of M and N, and then see where for the actual process, which of these makes the most sense. So the idea is to determine the optimum Y and optimum cost quality for a variety of industrial processes. Any process that produces a product at some desired, that should be quality level, is a candidate for Taguchi cost quality optimization. So it doesn't have to be a hardware product. When you say product, it could be a service, like I said, delivery, right? Delivery is a service, but you can apply the same principles. If you try to deliver exactly at the promised time, cost of quality is 0, right? But the cost of actual delivery is very high. Whereas if you deliver 2 or 3 minutes later than the promised time, the cost of quality now keeps increasing. However, your cost of delivery is now much lower. You don't have to hire so many people. The person doesn't have to speed and get tickets and have to pay for it and all that stuff, right? So that's the thing. You have to think about both the cost of quality and the cost to achieve that quality. So there's a cost of not achieving the quality and there's a cost of achieving the quality. And what we are saying is total cost is actually the sum of both. And that's what you should try to minimize if you're running a process and you're trying to optimize it. So you can do a lot of mathematical analysis, you can develop contour plots where you plot this optimum setting versus M and N values for various KQ and KM values. It's a classical, in fact I had an MTech student who worked on this and did a lot of mathematical analysis of various processes. But there are some case studies we can go through. Let me see, I'll try to find an interesting one. So I'll post this on Moodle. You can take a look at these in some detail later on. So this one that I like, somebody making cookies, right? You go to a mall, there's always a cookie store, right? And when you buy a cookie, what do you want? At least I want it to be soft and chewy. I don't want it to be hard and brittle, right? Anybody who likes it hard and brittle? You all like soft and chewy cookies, right? But for that, we know that the optimum temperature is somewhere between 350 to 400 F. That's where you run your oven. A lower oven temperature will minimize energy cost, obviously. But the cookie will be crumbly, it'll be harder, brittle. A higher oven temperature will increase the energy cost, and if it's too high, cookie can become very sticky also, right? So based on all this, 380 degree Fahrenheit seems to be ideal baking temperature to produce the best quality cookies. In other words, from a customer experience, they think that cookies baked at 380 F are the best, from a chewing experience. But what is the optimum setting for oven temperature? Is it 380 then? Well, to know that, you have to do this CQ-CM analysis. Let's say that CM, in this case, the actual cost of producing the cookies is determined by the heating cost. And let's set the heating cost at 350F as C subscript M 350F plus a multiplier A subscript M times the actual baking temperature minus 350 over 350. So basically we are saying that as the baking temperature increases from 350, the energy cost keeps increasing. CQ is a measure of revenue loss associated with crumbly cookies as well as sticky cookies. Since 380 is determined to be the optimum, then CQ can be defined as 0 plus, because at 380 cost of quality is 0 because that is a quality point, some parameter A subscript Q times, now it's TB minus 380 over 380 the whole square. Okay, so the total cost now is basically CM plus CQ, and this is what you want to minimize. So how do you do this? I mean, clearly the important ratio here is AM to AQ, because that gives you your weightage, right? So you can plot this total cost as a function of baking temperature TB for various values of AM over AQ. Now, if AM is very, very small compared to AQ, then obviously, what does that mean? Quality takes precedence, right? So your optimum temperature, when you calculate it, will be very close to 380F. On the other hand, if AM is a significant fraction of AQ, then it's going to be much closer to 350F, right? So that's the first figure on the left. So if you actually plot this optimum baking temperature as a function of AM over AQ, this is what it looks like. So if AM by AQ is 0, obviously the optimum temperature is going to be the optimum baking temperature. Similarly, if AQ is very, very low, it's going to be 350. If you know the ratio AM to AQ, you can use this curve, this line, to figure out where you want to be. So if the manufacturing cost is 10% of the quality cost, then the optimum temperature is 360F, right? So very simple. I mean, but I think it illustrates the concept very well. Obviously, when you do this in industry, it's going to be a much more complicated calculation. You know, how do you calculate manufacturing cost? Not of just manufacturing the product, it's of manufacturing the product at its ideal quality level, with not even a slight deviation from it. And similarly, how do you estimate the quality cost? You know, how do you know how much business you have lost because you are not producing the product at its ultimate quality level? So that's also not easy to calculate. It requires a lot of customer surveys. You have to keep track of, you know, how many customers you had at point A, and then some defect happened in your process, and then how many customers did you still have afterwards? Because customer retention is a cost item that's not easily calculated, right? And of course, you know, returned product, all of that is much easier to quantify. If a lot of cookies get thrown away by customers because they don't like it, or the store is not able to sell it, that cost is easy to calculate. But then, as I said, how many people are not ever going to come back to your store because they've had one bad experience? Why would they come back to your store to buy a cookie, right? They would go somewhere else. That cost is a lot more difficult to estimate, but you have to. So if you can estimate CQ and CM accurately, then you can very, very precisely identify where the process setting should be for that one particular parameter. Now, obviously, when you're selling an industrial product, there's not just one feature or one property that customers want to see. There may be 20 different properties that they want to see. You have to go through this analysis for each of those properties and see where they converge and where they diverge, and basically set or select process settings so that you are able to obtain maximum satisfaction indices for as many parameters as possible. So you may have to make a compromise somewhere. You know, a process setting that is good for one property may actually not be ideal for another property. Then you have to decide which of these two properties is more important to the customer, and, you know, choose that particular setting. So another way you can do this is a weighting factor approach. So instead of saying that total cost is a simple addition of CM and CQ, what if it's a product where quality is very, very important, whereas manufacturing cost is not? In other words, customers will pay a premium for, you know, a product that they really like. in that case, you can represent that situation by using this weighting factor beta. So you can write total cost as some beta subscript m times Cm plus 1 minus beta subscript m Cq. In this case, if price is the primary market differentiator, beta m will tend to 1. Okay, so because quality will now have much less weightage. Whereas if quality is the primary market leverage, beta m will tend to 0. So that now the manufacturing cost will have minimum weightage, right? You understand? So it's a simple application of a weighting factor. The weighting factor simply says how much weightage does a typical customer give to quality versus price. Is the customer willing to pay twice the price for a perfect cookie? Or are they happy to get, whatever quality cookie is, as long as they get it at a good price that they can afford? And interestingly, there are customers of both types, right? So that also you have to take into account. You have to know what percentage of your customers are interested in quality and what percentage of your customers are interested in cost. You may want to offer even two types of cookies. One premium cookie for the ones who are most interested in quality, and one low price cookie that where they can get three for 10 rupees or whatever. In general, of course, this beta parameter is not going to be 0. It's not going to be 1. Somewhere going to be between 0 and 1. But if you can again estimate this weighting factor accurately, your business is going to be a lot more profitable. So now if I take the same curve we had earlier, but now I plot this optimum baking temperature as a function of this beta m for some value of am by aq, which we just took it as 0.1. What you see here is, as beta tends to 0, the optimum temperature tends to 380, which is the optimum quality temperature. Whereas as beta m tends to 1, the optimum temperature tends to 350, which is the lowest cost manufacturing setting. So it's a very, very simply analyzable problem that obviously this is a illustration, but there's no reason why even the most complex industrial process cannot be analyzed the same way and for you to be able to arrive at the optimum setting. Let's see if I have another one that's. Yeah, we can take a look at this one. So this is another case where, you're doing machining of a slot for a product. The specification is 5 plus or minus 0.05 mm. The supplier who is making the product promises statistical process control. He says he can hold the mean at 5 and a standard deviation of 0.01. 3 sigma control limits are 4.97, 5.03. So the process capability index, CP parameter, if you're familiar with it, which is tolerance divided by 6 sigma, is 1.67, which is fantastic. Most people would consider this a very, very high quality process. However, IBM as a customer is not really happy with all this data. The supplier can show all the data they want, that they have a SPC methodology, they have a 6 sigma process. IBM says, anytime you deviate from that 5 mm, I have problems. I want you to give me product whenever, only at 5 mm width. But the supplier is not happy because if IBM will only take 5 mm slot width, they have to do a lot of adjustments on the line to get that ideal value of 5 millimeter. Now, it turns out that IBM does use that same cover for some low-end products. If it's a hard drive, they may be making the hard drive for home PCs or laptops, but they could also be making it for enterprise applications like airline reservations or banking systems, right? So what is the optimum strategy here for both the supplier and the customer to follow? So again, you can do this analysis of cost of quality and cost of manufacturing. Let's say that if your slot width is exactly 5, again the quality loss is 0 because you're at the ideal value. But the manufacturing cost is the highest because they have had to do a lot of work to get it to that point. So the total cost is 14. So you can, for various slot widths, you can estimate the quality cost, manufacturing cost, and total cost. and then you can analyze the data with and without weighting factors. So this is simply plotting as a function of slot width. The yellow line is the total cost, the purple one is the manufacturing cost, which is maximum at the ideal value, and the blue line is the quality cost, which is minimum at the ideal value, right? So this is without any weighting factors. So from this, the supplier and IBM together can make a decision on where they want to pick. I mean, the data would tell you that the minimum cost is somewhere at 5.01 slot width, right? Minimum total cost. So the supplier would say, take it at this value. Makes you happy, makes us happy. But IBM might say, no, I want it exactly at 5, right? So the other way you can do this is by using this weighting factor. Again, you can give some weightage to quality cost and some weightage to manufacturing cost. And this parameter alpha q can either tend to 0 or to 1. And actually, an enlightened customer would say, I'm not going to pain the supplier too much, because there is a cost impact that I'm going to have to bear. So what I will do is, I let this alpha q tend to 0 for hard drives that I'm only going to ship to the PC market, because quality is not the major differentiator. Whereas I'm going to let this alpha q tend to 1 for hard drives that I'm going to supply to the high-end server market, because I know their cost is not the differentiator, quality is. They never want it to fail. I mean, one failure, in airline reservations causes chaos and billions of dollars in loss. Same thing with banking systems. They don't care so much about cost, they care mostly about quality, whereas home PC users, laptop users mostly care about cost and not quality. I mean, if a hard drive lasts for a year, they're happy, or 2 years, they're ecstatic, right? But in enterprise applications, high-end applications, the minimum life they look for is 7 to 10 years. So quality is certainly king in that case. So again, you can now plot total cost versus slot width for various values of these parameters, alpha q value. So now the bottom curve shows the optimum setting for slot width as a function of alpha q. So if alpha q again tends to 0, the optimum setting is 5.03, whereas if it tends to 1, optimum setting is exactly 5, obviously. So depending on the weighting factor that you have derived, you set your process where this curve tells you. So that's another example of how the CQCM approach is used to set the ideal value. So anyway, like I said, there are some interesting case studies here you can go and take a look at. I mean, there's one on call centers. Call centers in low-cost areas are cheaper, but customer unhappiness increases. They don't want to dial in with a problem and have somebody in Pune answer it when they're sitting in New York, right? So the company has to balance the cost savings versus quality cost, because the customer may just walk away and buy from somebody else if they keep getting directed to call center in India when they really want help from somebody local. In fact, there is a trend where several US and European companies stopped outsourcing call centers to Asia because of many complaints from customers. So how do you establish a business case in this situation? You can again quantify it very well. You can look at savings per day because of your outsourcing strategy and business loss per day because of your outsourcing strategy, and you can establish your operational limits based on that. So actually, if you do it this way, if you know from your data analytics that percent of callers lost due to offshoring, you can actually plot it, or you can actually plot the cost per day, the net cost of offshoring, as a function of percent callers lost. But there are two different scenarios. What is the savings per call? If it is $1, that gives you a different reading, whereas if it's $10, it gives you a completely different reading. Because in the first case, the average loss of business per lost customer is $1,000, whereas in this, I think that should be okay. Right. So you can see that the results are now very different, right? And the optimum strategy in this particular case for offshoring really depends on how much do you actually save per call if you are outsourcing to India versus how many customers are you losing, how much business are you losing. Classic example of CQ, CM analysis. There is a paper that's interesting on Taguchi approach to airline overbooking. You know, how much airlines always overbook, but what is the optimum? Airlines would like to overbook as much as 25%, whereas customers want to see 0% overbooking. You know, if you buy a ticket, you want to be sure that you can have a seat. But that doesn't work for airlines because there are always last minute cancellations, people just don't turn up and they hate to fly with empty seats. Even one empty seat for them is an eyesore that they don't want, right? So, in fact, this analysis, which again they did the CQ and CM analysis, found that 35 seats should be overbooked for a 200 seat plane. Apparently that's the optimum. But the person who gets bumped off because of overbooking is not going to be happy. Well, airlines do make it up to you, right? I don't know if any of you have been bumped off flights. They actually give you a lot of money and vouchers and all that. So they try to make you happy, but still, if you have to be somewhere at a certain time, you don't want to get bumped off and have to take a different flight. So there is the reference textbook is Taguchi's Quality Engineering Handbook. I think if you're interested in quality, which you should, if you're ever planning to enter industry, you should take a look at this book. Well, there are also papers you can just access online. Certainly, Science Direct has a lot of papers you can read. Even Google, if you just do a Google search for Taguchi quality, you'll get hundreds of thousands of or billions of papers to look at. So I had this student who did an MTech project on, and there's also a journal published paper that we published on process optimization based on Taguchi quality loss function concept. But a lot of reference. So I'll like I said, I'll post this on Moodle that you can take a look at it at your leisure. So Taguchi was a practical visionary who simultaneously conceptualized and quantified cost of quality. His major contributions, as I said in yesterday's lecture, were that he really worked a lot on design of experiments. And he made the point that engineers should decide which parameters should be included in the design of experiment. They should know if there are 10 parameters, each can vary at 3 levels. The mathematician will tell you have to do 3 to the power 10 trials. An engineer should be able to tell you, of these 10, which are the 5 most important parameters. So that even if you want to do a full factorial experiment, you only have to do 3 to the power 5. But he also came up with this Taguchi design of experiments where he showed that you can get the same results with a much reduced number of experiments. In fact, 5 parameters, 3 levels, you can do your analysis with just 27 experiments. It's called the L27 matrix. I don't think we had a lot of time to discuss about the DOE part of Taguchi quality, but he also made substantial contributions to the most cost-effective design of experiments which will give you the maximum data with minimum number of trials. So you can read up on that also. So, but his focus was all on quality and cost of not achieving quality. Whereas in industry, you have to counterbalance that with cost of manufacturing. Typically, it's true that you get what you pay for, right? I mean, if you want high quality, you have to pay more. There are very, very rare instances where that doesn't apply, but those are the exceptions. Typically, if you want higher quality, you pay more, right? CM, the cost of manufacturing can be calculated based on internal metrics. You know what the cost is to manufacture a product at a certain quality level. But estimation of cost of quality is mostly customer driven. You have to work with customers to understand that, because the customer is the ultimate decider of quality. Quality is not an internal metric. Whatever a company may claim that they have, quality certification, that they have Six Sigma control, absolutely means nothing. The customer decides whether you're making a good quality product or not. As I said earlier, customer dissatisfaction and associated costs are hard to quantify, but not impossible. It does require a commitment to do it. If you have that, you should be able to do that. So what we actually did in that paper, in the thesis and in that paper is take the Taguchi cost of quality model and then integrate that with the cost of manufacturing model and looked at various scenarios of how you can actually optimize the process and the product, taking both into consideration, cost of quality and the cost of achieving that quality. Okay, so that concludes the module on quality. I think it's something you should show familiarity with in your interviews. If you can talk confidently about quality, I think that'll be a huge plus, because a typical college graduate, whether undergraduate or postgraduate, has no clue about quality. Unfortunately, our curriculum doesn't even include statistical process control as a module. Any process control that you're taught is all deterministic. It's like, we have all these courses in process control, but they all tell you that, you take this data and you take this action, you do feed forward, feedback, all that stuff, and you can precisely control your process. That's absolutely not true. Every process fluctuates like crazy. And the only way you can control a process in reality, in real life, is allowing for this fluctuation, monitoring the fluctuation, and controlling the fluctuation, not the mean value. Mean value will not change much, but the fluctuations can drive you crazy, and well, more importantly, it will drive the customer crazy. So you cannot afford to have those. Okay. Any questions? Okay. So I guess our next class is Monday at 12. See you.